Make sure you get your name on that. Anybody that's not getting our weekly newsletter, we send out a technical, it's called Monday Morning Technical Notes and Coffee. But if you're not on the email list for that, we have a sheet for that too. We'll be happy to add you to the list. John Liptak from the Tower Service has brand new calendars to get started. We've been in business or been in operation for 5 years with the Engineering Academy. Josh Bond with Bond Broadcast Services. And Josh, I want you to just say a few words to him.
Thanks, Larry. I don't usually need a microphone because I'm pretty loud, but just wanted to thank you all for coming. I'm taking the class just like everybody else is, and I'm really impressed with everyone we had yesterday. I'm looking forward to hearing from Kirk, but I believe I've passed out a card to everyone that's here. If you didn't get one, I'll have them at my seat right there in the middle with the donut bag. We're also RF specialties, so anything from Nautel transmitters, Shively antennas, Omnia processors, to pretty much anything else you could need, we can provide for you at competitive prices. Appreciate the opportunity to do business with everybody here. Also, we operate a full-service repair shop in just outside Dallas, Texas. Service a lot of Marty gear, Mosley gear, STLs, exciters, Symmetrics mic processors. So, any opportunity that may arise for you to need repair service, we'd appreciate the opportunity to help you out. So, once again, thanks for coming, and great to see you all here. And I'll hand it back
to one of my really good buddies I've known for a long time, Mr. Kirk Harnack. Kirk is with Telos Alliance, makers of a lot of different equipment, processors, and telephone systems and all. And he was so gracious to come down and bring a few of these. I don't know which one of these are the door prizes. He didn't tell me. I think it's a surprise.
I think it's the exciter because that came for free.
Oh, yeah. Okay. All right, Kirk, program's yours.
Thank you so much. You guys remember the great company Gentner, right? And who was the guy with the British accent that worked for Gentner? I had his name in my a few minutes ago. Now I can't remember it. I'll think it'll come to me. Dave somebody, I thought. Anyway, kind of short, round guy with a British accent. Anyway, so he was demonstrating. You guys remember, of course, their single-line frequency extenders gave you more bass across the phone line. And then they had the two-line extender. And that year they introduced the three-line extender. 3 POTS lines, no waiting, and you got supposedly about 7.5 kilohertz worth of audio. And when it worked, it sounded pretty good. So Dave Pedersen, it's spelled like Peterson, but it's pronounced Pedersen. Dave Pedersen, he was describing this 3-line extender to a couple of what looked like, obviously, farm broadcasters from Iowa. One of them was dressed in overhauls, and one was dressed in coveralls. And you guys know the difference between the two, right? Not every audience I talk to does. And so Dave described that, and these two guys just thought it was the coolest thing. And they gave the audio demonstration and everything. I'm just standing back there like a kid in a candy store. You know, I'm young, NAB, what could be better, right? And Dave got done with the demo. He walked off. One of these, the guy in overhauls turned to the guy in coveralls, and he said, "You know, this here digital's the coming thing." And what was that? Was that 25 years ago, probably? About that? What year was that, you think? It was 89. 89? Yeah. Wow. Wow. Okay, so what's the math on that? 27. Or, wow. Wow. This here digital is the coming thing. And so those guys were absolutely right. Yeah. They sure were. So let's buzz through this really quickly. By the way, I guess I should ask, how many of you have some audio over IP studios? Okay, so that's at least half. Okay. How many of you are in TV, by the way? 1? 2? Eddie? Okay. Okay. All right. We'll spend less time on the TV aspect. Let me crank that down a bit. Eddie, how's that? It's going to be all right? Okay. Good deal. The first few slides here, I'm going to buzz through pretty quickly. Just want to get us all on the same page, and then we'll study a bit more in depth. You know, the guy that started Telos, good deal. Okay, so Steve Church had a penchant for invention. You might recognize the bottom product, the original Telos 10. This was the very first broadcast product that had DSP in it. In fact, at the time that Steve developed this, there were only 5 DSP chips in America. he got a free one from Texas Instruments. And then he got some help from a professor at, I want to say, whatever the university is in Indianapolis. It's not IU, but, well, anyway. And so they worked on some code together to improve the operation of a telephone hybrid, to get rid of any audio coming back that had been sent. And so that experiment became the Telos 10. Then, of course, the Telos Zephyr was the first, I think the first product anywhere to have MP3 in it. Because when Steve went to Fraunhofer to license MP3, they hadn't licensed it to anybody else. We were the first licensee of MP3 anyway. And Steve negotiated with them for basically a worldwide, non-exclusive license to MP3 for $125,000. And I think they financed $100,000 of that for us. He could, by the way, we could have had, according to the story, according to legend, Telos could have had worldwide exclusive rights to MP3 for $250,000, but we didn't have $250,000. And then along came audio over IP, which Steve and his crew basically invented. At the time, we had CobraNet and EtherSound. Neither were acceptable for live broadcast. You couldn't talk into it and hear yourself back. You know, the latency was way too high. And at the time, those were not routable. I believe they are now, but at the time, they weren't routable. So this is the very beginnings of audio over IP, the very first console we showed it at NAB. And there's the development team that worked on it. Greg Shea is named on the patent for the clocking system because, you know, what do they say? A man with two watches never knows what time it is, right? So everything has to be synced together. That's true for all digital stuff. And we had to figure out how to make really, really accurate clock over a jittery network. Now, that's kind of been done in the past. ISDN actually did that. Your home cable modem actually does that. And ISDN certainly did that. But this was a new special case, so we actually have a patent on that process. Not a patent on LiveWire per se, but just on the clocking process. So Steve reminded us that there were all these different connectors out there, and you guys have dealt with every single one of these. XLR, RCA, DB9, DB15, a quarter-inch phone, mini phone, RJ45, and then all the different proprietary standards over fiber and copper and just all this stuff. And remember where audio over IP started. It was with the original Ethernet. That's a rendition of the original drawing of how Ethernet could work. So rewind yourself back to 1999, right? So this is when, let's see, Windows 3.11 was king. You remember that? If you're going to install Novell, you had a stack of 48 disks to install Novell with? Well, we wanted to ask, what if a network that we used to transfer files and share hard drive resources, and that was kind of barely working at the time, what if we could make that share audio? What if we could do that with very little delay, with high reliability, with pro quality audio? Well, in '99, that seemed an enormous task. I mean, sometimes you hit print and the printer doesn't do anything. So how are you going to get real-time audio across a computer network? And remember, the collision light on your hub. I worked at Scott Studios starting in 95 and 96. And remember, everything was a hub then. And this was the first computer network I'd ever really dealt with, except for a little one at my home. And remember, the more computers you would add to the network, the more the collision light would light up. And after a while, the network just seemed really boggy and slow and just wouldn't do much. Well, how's this going to work for audio? Well, Steve had heard rumors of Ethernet switches that were deterministic in nature, and they would determine who was where, and they'd build an ARP table, and things would go where they were supposed to, not just be broadcast everywhere. So that kind of played into this feeling of maybe there's a way to make audio over IP work. And then we borrowed from something bigger, and that was Ethernet. That was the computer industry. I've got a little story about that. Some years ago, early in my days as the U.S. sales manager for Telos, I was tasked with going to the NAB radio show in the fall, and whatever year that was, it was in San Diego. Well, I was excited about going to San Diego, but I wasn't excited about paying the room rate at the hotel. So I found a cheaper hotel down the street, and I so the morning came for me to set up. It was just me. We didn't have a crew. I was the setup crew. I was going to be manning the booth the whole time. And so I got my gear outside, called a cab, put the gear in the cab, got in the cab. The driver says, "Where do you want to go?" And I said, "Well, I guess the convention center." Yeah, I guess the convention center. I forgot where it was. So we drove to the convention center, I stopped, I was about to get out, and I see all these guys walking to the convention center, and they all have T-shirts and jackets on that say things like HP and Dell and Cisco, and I'm thinking, no, this isn't my convention. I said, I'm going to the radio convention. Oh, that is in the Hyatt Hotel. Okay, great, let's go there. So we went around the block to the Hyatt Hotel, and it sure made me think. I got in there, and it wasn't even a whole ballroom. It was, they had half of it cordoned off. So it was half a ballroom. I'm thinking, you know, the radio industry is really pretty small compared to those guys taking up the convention center. And it's like that. You know, this is why we've been borrowing from other industries for years. 600 ohms came from what? The telecom industry, right? Punch blocks came from the telecom industry. And now we get our technology from computer industry. So the very first audio over IP began as a snake application. There was a radio station in Ashtabula, Ohio, not too far from Telos in Cleveland, and they had a problem. They had a studio building, and then a parking lot, and then a transmitter building, and a tower, 400 or 500 foot tower. And they had copper wires underneath the parking lot connecting the two, and they had satellite receivers at the transmitter building, RPU receivers, plus they had the audio processing and transmitters in that building. And of course they had the studio stuff in the studio building. And you know what happened every time lightning hit with differential grounds and the 5532 ICs that were, you know, driving these wires, it wasn't pretty. They should have gone back to tube technology, I guess. Well, they had enough room in the conduit to pull a piece of fiber, so they did. And we used a little media converter at each end to convert the fiber back into Ethernet and put a node at each end. And they had 8 beautiful stereo pairs in each direction, and it was perfect. And to my knowledge, that was an iHeart, or at the time, Clear Channel station. I think they still are, and I think they're still using this tech. They may have upgraded their nodes since then, but because that's been, boy, 2003 or 4. So it's been a while. So that was the first application, was a snake. Then some early applications, WOR in New York. The middle picture there is WEGL in Auburn. That was the very first installation, and we didn't have a manual written. So a guy named Mark Johnson, not the same Mark Johnson that's talking this afternoon, but a different Mark Johnson, was the engineer for the station. And so I drove down there to help him install. Got there, and he said, "Great, glad you're here. Good news and bad news." I said, "What's the good news?" "Well, good news is me and my girlfriend wired the studio already for this stuff. It's really easy. It's just Cat5 cable." I said, "Okay, good. What's the bad news?" He says, "FedEx lost the console." "Okay." I said, "This is the college town, right?" He said, "Yeah." He says, "That means you have beer and pizza." He said, "Yeah, absolutely." So we had beer and pizza for 2 days, and then the console showed up. And within 4 hours of the console showing up, we had it plugged in. Now, we had no manuals, so that's why I went there. And literally 4 hours later, it was on the air. And then an early station in Riga, Latvia, right there, Radio Skanto. So now there's this stuff all over the world. There's literally about 70,000 live wire devices operating right now as we sit here. There are probably close to 500,000 live wire audio over IP streams running right now all over the world as we stand here. There are over 7,000 Axia audio consoles. Now that's just the Axia stuff. I mean, Wheatnet and Wheatstone, they've got plenty of consoles out there. Logitech has some consoles that were running audio over IP. Of course, anything that's running, you know, Dante, all your ProSound consoles that are out there. Oh, and then you've got Ravenna. You've got Lavo consoles and others that are running this kind of technology too. So when people still occasionally come to me and wonder, well, does this stuff really work? Yeah, it really works. And if you learn about it, you're really going to like it. If you don't learn about it, it may still be frustrating as the first day that you ever looked at it. Steve Church said, you know, one day, every device is going to have an Ethernet jack on it. And that Ethernet jack, we could use that, not just for remoting into it and controlling it and programming it, but we could get audio in and out of that same jack. Or that people might put a separate jack on there. So Jeff Welton, you guys have a product that has a live wire on it? Several, okay, yeah. And you were the first and maybe still the only transmitter manufacturer that has live wire. Okay, okay. We've had other inquiries, but so far nobody's, gone through this much trouble to make it happen, besides you guys. Satellite receiver from IDC. There's, every NPR affiliate, to my knowledge, has LiveWire, whether they have consoles or not. They've got a jack on the back of their receiver. A whole lot of Westwood One receivers out there. I'm not sure which one have them. Now there's even a microphone. Audio-Technica has one, and the LiveWire electronics are built into the mic. So you just take a power over Ethernet cable, plug it in the microphone, you browse into it. I think you use Bonjour to find it. And then you browse into it and you program it with an IP address. And no, excuse me, it's AES67. It's not LiveWire. It's the new AES67 standard. Neumann has one, although theirs is a separate box. It's a rack-mounted box that the mic plugs into because they got to be expensive and different. So yeah, so many things have this now built into it. And if you haven't, if you want to come really up to speed on it, even though this book is 8, 9 years old now, it's still 99% totally relevant. So literally, we wrote the book. Steve Church and Skip Peasy wrote the book on audio over IP. So let's move to the meat and potatoes here. You know what, that wasn't bad. Let's go ahead and cover this. So obviously, with audio over IP, and by the way, when I say AoIP, audio over IP, even though the industry doesn't really have strong differentiation terms, I'm really talking about in-studio audio over IP. So this is not outside the studio. This is inside in a controlled environment, your equipment you have total control over. Now, later on, we're going to talk about SIP and voice over IP, and that's stuff that's out of your control, and we'll see how that works. But obviously, it's digital audio that's been packetized, so it's almost the same ones and zeros that you get with an AES stream. It's just that we bind them into packets. We stuff them into packets. Carried by, there's nothing special about the packets except that for our live streams, our low latency streams, the packets are very small. Like they have literally 24 samples of data, 24 bytes of data. So the header is bigger than the payload, but that's how you make it operate fast. Which is, that's not how we usually do things in computers, right? We usually try to fill the packet up to the MTU, the maximum transmission unit. And it does require a high-performance IP network. So this doesn't work over Wi-Fi typically yet. There's new Wi-Fi's coming that it may work over. The audio, we had to do some standards picking here, and rather than complicate the broadcast world with a whole bunch of different sample rates and stuff that may frustrate you, 48 kilohertz sampling and 24-bit depth. I don't know of a broadcaster for whom this is not good enough. Sure, there are some recording studios that says, oh, we cannot have less than 96 kilohertz. Oh, okay, fine. And 24 bits of bit depth is something like, what is that, 120 dB of top to bottom? Yeah. Okay. Standard IP packets, we use different types of packets for different functions. Sending audio, we want that to be very low latency, and we're on your own network, so we don't need to really handshake. We don't need TCP to test the speed of the connection and to handshake. And did you get my packets? Yeah, I got your packets. Okay, I'll send you more packets this time. Okay, send me more. We don't need all that. We just send UDP. Once an endpoint requests a stream, we just send it until the endpoint either doesn't exist anymore or says stop sending. Whoops, didn't mean to do that. Let's go back to that one. We use IP multicast a lot, and I'm going to explain that in just a minute. And to get the low latency, we use very small packets, and we use quality of service so that when the packets get to a switch, the switch says, let's see, email, file upload, or audio. I'll do the audio first. So the audio gets absolute priority through a switch. Bottom line is the end-to-end delay is less than 3 milliseconds from microphone to headphone. And that's more than 5, 6, or 7 milliseconds. A lot of people start hearing that as a comb filter effect in their ears. And up around 8, 9 milliseconds, it's not pretty, and 20 milliseconds is terrible. And now that's if you can, that timing applies only if you can hear yourself live and hear yourself somewhere else, like multipath, right? So multipath in FM wouldn't be an issue if your radio couldn't hear the main transmission. If it only heard one bounce, who cares? But if your radio hears the main transmission and a bounce and another bounce and another bounce, then that's multipath. Your brain doesn't deal with that too well either. So if you hear your own voice through several different delayed transmission paths, and by the way, through the air, it's about 1 millisecond from here to here. So the 3 milliseconds that AoIP takes doesn't mess with your head. But you get up more like 7, 8, 9, 10 milliseconds, and jocks go, I sound funny. I sound like something is sucked out of my head. Well, that may be good for you. So I'm going to use some drawings here using red as analog or AES connections, and I guess is that blue or purple? What do you think? Purple? Purple? Okay. Purple for audio over IP connections. So let's see here. We start with a CD player. We have a node which converts between the IP world and then the AES or analog world, and then a switch. So we have legacy devices. So if you have some things that don't speak LiveWire, and I'm going to say LiveWire because I'm so used to it, but I'm also meaning AES 67 because that's becoming a ubiquitous standard. To get on the network, you got to connect to a node. Just connects the audio, converts the audio into IP. And it either does analog, does A to D, or does an AES, which does a sample rate conversion into digital 48 kilohertz 24-bit. Then it packetizes that payload into small 24 sample packets. The user assigns a channel number to that stream, and that channel number is algorithmically used to assign a unique multicast IP address. A couple things about this. First of all, if you started it with AES audio early in your career, maybe in the late 80s or early 90s, the phrase sample rate converter got a pretty bad rap because the sample rate converters available at the time were pretty bad. They operated oftentimes at only 12 to 14 bits of resolution. So you take 16-bit audio, they do a bunch of math at 12 to 14 bits, and of course what comes out is now sample rate converted through a lower quality math function. Nowadays, sample rate converters operate typically at 20 to 24 bits, so that's way better than the 16 bits, and almost as good as the native audio going in and out. So sample rate conversion is no longer a bad name. It's used all the time, and it's used to good effect. So even if you feed 48 kilohertz AES into our node, we're still going to sample rate convert it to make it perfectly match up with the timing of the Axia system. And the thing about the unique multicast IP address, let me see if I explain that a little bit later on here. The packets that are generated by the node are standard packets. They have tags for UDP, RTP, which is real-time protocol, which basically just means they're time-stamped. So when they're received at the other end, they get put back together in the right order, even if they arrived in the wrong order with enough of a buffer time. And a very high quality of service, or QoS figure, and the unique multicast IP address per source channel. Again, let me see if I explain this. Here we go. Okay, so here's how multicast works. There's a whole range of IP addresses in the IPv4 range. They start, I believe they all start with 239. There may be another range as well.
224, 239.
Oh, okay, there you go. We use the 239, which is why that's what I'm familiar with. So if you give a channel in LiveWire a channel number, and I'll show you how I do that in a minute, instead of making you, and by the way, the first version of LiveWire made you come up with the multicast IP address, and that was a whole lot of typing and a lot of chance to get things wrong. But you come up with the IP address, we have a little algorithm, it's really pretty simple, we can do it in a spreadsheet, that just turns that into a unique multicast IP address on the network. So you never have to worry about, as long as you don't give two things the same channel number, and the channel numbers can be anything between 1 and 32,768, that's the top number. Then we'll give it a unique multicast IP address. And multicast works this way. The stream is generated and it goes to the nearest switch. And if it's a multicast aware switch and it's a multicast IP address, the stream goes to that switch and it stops. Actually, that's not quite right. It goes to the switch that is, if you have multiple layers of switches, like a central switch and then some edge switches, it goes to the core switch. It's transferred to the switch that is the querier, that kind of keeps track of all the multicast streams. And by the way, in switch parlance, these are called IGMP groups. So the IGMP stands for what? Internet, what's that?
Messaging protocol?
Yeah, IGMP, Internet Group Messaging Protocol. So And switches have a limit as to how many IGMP groups that they will keep track of. For example, this little Cisco 2960 will only keep track of 256 IGMP groups. That means you can't have 10 studios operating through one of these switches, but you can do 2 or 3. It'll work fine. Okay, so the packets go to that switch and they stop there. They don't go anywhere else until somebody else requests that stream. They said, hey, switch, I'm looking for stream this IP address. And the switch says, oh, I've got that. I'll give you a copy of it, and hands it out. So the source streams are multicast, and we use source advertisement so that if I was, oh, hello, what did I do? Did I stop that somehow? Oh, I see. Sorry about that. Along with just pushing this multicast stream to the nearest switch, we also push out, every device on the network pushes out a broadcast packet that advertises, here's the stuff I've got. So you've got nodes, you've got Omnia 9s, you've got my laptop here, all pushing out to the network every 10 seconds a packet that says, here's the stuff I've got. Here's the IP address of it, here's the friendly name of it, and maybe some other metadata about it. And those are broadcast packets. They go to every device on the network, and then every device on the network receives these packets, compares it to a table of what they've got, and if it's new stuff, they add it to the table. So every device on the network knows about every other device on the network, knows about every stream, and knows the friendly name of it, and knows the multicast IP address of it. So that's why when you go to one of our devices and you say, I want to subscribe to something, you hit a little button, you get a drop-down list, and it shows you everything that's on the network. You just click on it, and bam, now you're subscribed to it. That easy. With AES 67, by comparison, there is no advertising. There's no discovery, as they call it. And so you have to know about it. You have to type all this information in and not make any syntax errors when you're typing it in. But it does make WheatNet talk to Livewire, and it makes Ravenna talk to WheatNet, and so forth. So when something, let's say we want that stream to come out to that node and be fed to some speakers, we browse into that node. We tell it, I want to subscribe to whatever stream it is that we want. And then the node requests that from the IGMP querier switch, and the switch sends it. And I think I just said that. Sends that to the device. The node receives a stream, analog or AES, and delivers it to the desired audio output. So a PC, Windows, OS X, Linux can source or receive audio on an AoIP network. And so this can eliminate sound cards. Earlier, let's see if that's not what I wanted to do. I'll just demo it later. When you came in the room, you heard audio playing through the speakers. It was coming out of this laptop. Wasn't using the sound card. I was just using the Ethernet connection over to a switch over there, and I'm running the IP audio driver. Mac OS thinks that there are 8 more sound cards in this computer than there really are, because the 8 sound cards are virtual and they're just a driver, which is all the OS is talking to anyway. You put a sound card in a PC and you got to install the driver. And so the OS talks to that driver. And it's bidirectional. You could receive them in here as well. This makes it really convenient to get audio in and out of the network. Usually I will add a second NIC on the computer and have that available for the Axia network. So at my own radio stations, I don't think Larry mentioned, I'm part owner of 8 stations in Mississippi and now 3 in American Samoa. I'm part owner. I own the part that doesn't make any money, which is why I work for Telos full time. So the IP driver, just like the hardware, can send audio and subscribe to network channels as well. And there's an example of the Linux driver. So that's running in our Rivendell systems right there. In fact, that's audio coming out of the automation and onto the network. So it's a source send to network. There's the friendly name, RD for Rivendell, WNIX. There's the channel number that gets converted into a multicast IP address. And the way I do channel numbers, 104 is the last octet of that computer's IP address. So it's 10.216.0.104. So if I use that, and then I give it either 1 digit or 2 digits, this case I gave it 2, to represent which output it would be. This is a single channel driver. There can be only one, so it's channel number 10401 on that network. I can go anywhere else on that network, subscribe to channel 10401, and I will hear the output of the WNIX Rivendell. Also, we subscribe to some channels because we use this machine to record across the network. So we record CBS News and Fox News and whatever else comes up. And we can also remotely or locally change that subscription. So right now, subscribe to channel 211, which I happen to know is off of node number that ends in .21. It's 10.216.0.21, and it's the first output from that node, which is probably a satellite receiver that we're recording. So anyway, that's just a quick look at the Linux driver. There's the Windows driver. I think you can get up to 32 ins and outs at the same time. A lot of software that comes from Telos, like the iProfiler software that is used for logging, or any of our streaming software, you buy the software, it comes with licensing of a channel on an IP driver. So you don't have to buy the IP driver separately if you get those products. I know that says up to 24, but I think we're up to 32 now. Anyway, so these are all the sources from the PC to the network, and then from the network to the PC. Just like a distribution amp, a single source stream can be subscribed to any number of devices on the network, up to the limits of the ports on the switch, which is way more than you're going to need. As I mentioned earlier, it's the number of network sources total is limited by the IGP group table size. 256 for that switch, but there are large switches that you can get 10,000 IGMP groups, and there are some facilities that use close to half of that. Radio Free Europe and Radio Liberty in Prague, Czech Republic, have 4,000 sources and about almost 2,000 destinations on their network. And it's all redundant. They have a switch on one floor and another switch on the other floor, and they're all working all the time. And in fact, we had to figure out a way, well, how are we going to make switchover automatically? Like, let's say the third floor big Ethernet switch dies. How do all the studios just automatically start using the second floor Ethernet switch? Well, all of our end devices use the packet that comes in first. In other words, if they're receiving duplicate packets, but one arrives later than the other, we'll just use the first one and discard the second one. So in the backup Ethernet switch, which is huge, it's like a Cisco 6500 series. We added a fake hop to all the packets. Take a fake. We decrement the hop number or increment or whatever you do. Anyway, we make it seem like it's taken longer, even though it hadn't taken any longer. We make it seem like it has because it's got a higher hop number. Okay, and so it just switches automatically. Understanding configuration of a node answers a lot of questions about operation. So you browse to the IP address of the node, and you enter your security credentials, and you configure it. So let me get to this. So sources. Trying to think of the best way to explain this. So let's say that you've got, on one of our newer nodes, you've got 4 physical inputs on it. And so you plug 4 things into it, and you give them names. So these would be all connected coming from tuners that are in the rack. And so there's what we name each of them right there. In the same node, it also creates streams. So these are the destination. These are what you want to subscribe to come out of the node. And actually, I'll tell you what, let's look at that again. So here's the sources. And on the new nodes, you can have 4 stereo or 8 mono or any mix of that you want. So I need a bunch of mono stuff because I got a bunch of satellite receivers that are all news stuff. So these are all the inputs, 1 left, 1 right, 2 left, 2 right, and so forth. Gave them all friendly names and gave them all channel numbers on the system. Gave them a stream type, either a live stream, which is low latency, or a standard stream. And the difference there is that PCs are a lot better now, but when we came up with LiveWire, a PC couldn't generate or subscribe to a live stream because it's 2,000 packets per second. Each one's just 24 bytes of data. So we needed a stream that, if you didn't mind a little latency, and hey, it's already got almost a half second of latency going to the sky and back, right, on a satellite receiver. Who cares if there's an extra 20, 30, 40 milliseconds of latency? So a standard stream is 200 packets per second. And so PCs can easily generate or receive 200 packets per second. So, but you wouldn't want to talk and hear yourself back with 30 or 40 milliseconds of time between that. That would just drive you nuts. So standard streams exist for compatibility with PCs and stuff that you don't need to have to be a live stream. If you're going to pass, for example, our streams over an IP radio connection from, say, studio to transmitter, you don't want to use a live stream. That's 2,000 packets per second. Some IP radios just go, ah, when they have that. So standard streams are very standard looking. Here's that drop-down list. So you click the subscribe button, and there's a list of everything that's on the network. You just click it and subscribe to it. No typing. You just click it. There it is. And bam. And that sends a message to the querier switch, hey, I want you to send me this stream. And it does, and the stream appears. And then you've got a metering page that you can look at to verify stuff. And then if you need some, these are all the deep settings, clock. And now that we're compatible with AES67, there are clocking items on here, like for PTP clock and stuff that's needed for AES67. And then the network setup on our new node, you can have there are two network interfaces, and one can back up the other. Or one can be assigned to be just a management port. So you can put one port on your LiveWire network, and the other one could go to a network that has a Wi-Fi hotspot on it. And that would be fine, because there's no LiveWire audio on there. Okay. You know what? We probably don't need to go through this, because I think you guys get it. But here's where we change that channel number. So there's any channel number between those numbers. 3501, 3503. Oh, yeah. So right there's the math, in case you're interested. So the multicast range. Oh, this is kind of cool. You may have heard that modern-day consoles can do mix-minus automatically. And we certainly do. We may have been the first people to do that, because we could. And without going into this in too much detail, whenever we have a channel number, let's say we have channel number 3501, 99% of the time, that's channel 3501 from the source. Well, duh, it's coming from the source. But let's say that we wanted to send a mix-minus back to that device. And we wanted to be able to do that from Studio A, but sometimes we wanted to use that device in Studio B and also send a mix-minus to it. Not in addition to, but instead of Studio A. So now we want this device to get its mix-minus feed from Studio B. And then we want to subscribe to it on weekends from Studio E. How do we, without reconfiguring the device that's receiving the mix-minus feed, how do we make that happen kind of automatically? Well, we have this notion of a channel number from the source, like from the codec, and we have the notion of a channel number that goes to the source. So a stream can be a from stream or a to stream. And the difference in the multicast world is that it gets either a 192 or a 193 as the second octet. What this means is that, let's say we have a codec, and we're going to take the same LiveWire channel that it generates. Let's say 3501 is coming from some codec. We tell it to receive channel 3501 to the source, not from the source. So any device on the network that generates channel number 3501 to the source gets picked up by that codec. Now, two at the same time won't work, and that's why our consoles are also aware if a device is already subscribed elsewhere. And then you can't, if it's already in use elsewhere, which is a metadata tag, then we don't generate a new mix-minus to that device. You have to unload it from one console and reload it from another console. Now, we can do all this automatically through Pathfinder. There's ways to get that done. But point is, the disc jockey, nobody at the station has to go change, oh, now I got to feed mix-minus from Studio B to this codec, otherwise the guy can't hear me at the stadium. It takes care of itself. So it's really, really smart. But that's why we have a from the source and a to the source. And then the third octet ends up becoming the LiveWire channel divided by 256, and then finally anyway, it happens automatically. There we go.
Do you associate a port number with your audio feeds?
They're all live wire channels use the same port number, so they're not differentiated by port number. They're differentiated by multicast IP address. Yeah, good question though. We could have done that, but then it turns out we have no need to. Just one port is all it takes. It's just like you can be running 72 tabs on your browser. They're all working on port 80, you know, of your IP connection. So I already explained that about the IP packet stop. And what I want to do here is, I mentioned every node maintains a table of everything on there. Let's see if we can skip ahead here. Because what I want to do, since we're all on the same page on this, I want to get to the telephony and voice over IP. I guess I should point out that the notion of a mix engine. So let's say you've got an audio console and we have a mix engine. So the mix engine attaches to the network, and we typically will attach it to a gigabit port. Now, most switches nowadays are all gigabit anyway, but in case you have one that's not, the smaller nodes will never use more than 100 megabits. In fact, their max typically is about 70 megabits per second. So they can go to 100 megabit ports, which are now pennies on eBay, basically. But a mix engine may subscribe to 40, 50, 60 things and may generate that many going back. So we need a gigabit port for it. And the mix engine then falls under the control of a console. So what happens is the console basically tells the mix engine, hey, I want to have mic 1, mic 2, and mic 3, and turntable 1 and 2, and automation 1 through 4, and CBS News, all on my console. So the console tells the mix engine this, and the mix engine then tells the switch, hey, subscribe me to mic 1, mic 2, mic 3, blah, blah, blah. All those things that you want to subscribe to. So all those streams come into the mix engine, and then the console tells the mix engine what to do with those things. Multiply this by this factor, and this by this factor, and mix these things into this bus or that bus. So adding more consoles is pretty simple. You just add another mix engine to the switch, add another console, and voila, you have a whole other studio ready to go on air relatively simply. I've got a pretty cool picture example. Now, disruptive technology. Maybe you've heard this term, disruptive technology. Back in 1999, Amazon.com was pretty disruptive technology. They would print books on demand and ship them to you. And the other book publishers said things like, oh, that won't work. We've never done it that way before. So when Steve Church announced Livewire, of course, people said, it won't work. I was at an SBE meeting in New York City where you'd think they'd know better. And I demonstrated it working and played audio, several audios, and went through the whole shebang. Guy in the back raised his hand and said, that won't work. Your collision light's going to be on all the time. I said, well, you know, if we had a collision light, you'd be right. But there is no collision light on this switch because nothing collides. They're deterministic switches. The next thing people say is, well, it may work, but you don't want that. And then they say, well, we do that too. So that's kind of been our story. Oh, speaking of Radio Free Europe and Radio Liberty, this is their new control center. And this has probably been 8 years ago now, in Prague, where they moved from an old facility, which was, by the way, full of Soviet bugs, over to a new facility, which it may not be as full of Soviet bugs. I think it was built all by U.S. contractors, which who knows if that's good or not, I don't know. But they're all, this is where there's 4,000 sources and 2,000 destinations. Let's see, what story did I have? Oh yeah, this is a Cumulus facility in Baton Rouge. And my good friend Gary Klein insisted on using a competitor's product there, not going with ours. And he used the product that was designed to save you on wire. And they advertised for years in Radio World with a little man standing next to a whole bunch of reels of wire, demonstrating how much wire it would save you. I think it was 9 engineers for 3 months to build this, eating bad hotel food and traded out hotel rooms in Baton Rouge. You know, compare that. I mean, I'm not sure if Belden loves us or hates us because Steve Lampton says he loves us. But this networking technology is just spread everywhere. This is in Taiwan. It's a classical music station. That's 1010 Winds in New York City. They've since switched to a different system because my buddy Chris Tobin's not in charge of that anymore. Let's see. Oh, this is Andy Linton in Waterford, Ireland. Back in the early days of Livewire, I would tell engineers, this is going to save you a ton of cable and a ton of installation time. Now, I said that because I thought it was probably true, but I really hadn't heard any feedback on that. So about 5-6 years ago, I got several engineers together at a nice restaurant in New York, and then interviewed Andy Linton by phone, and asked them, did you really save any money? And Andy said, in 2007, we completed a 3-studio installation using a TDM-based digital system. During this, we utilized over 3,000 euros of multi-core cable and terminations. It took 3 men, 3 weeks to install. A year later, in 2008, for the same radio group, we installed 3 studios at another location, this time using IP-based console and routing system. It was ours. On this installation, we used 1 box of Cat5, 70 euros, 150 euros worth of terminations, and it took 2 men less than a week to get 3 studios live. So yeah, that was a huge savings. This is Matt Galick. He was, at that time, the radio engineer for the Metropolitan Opera in New York. He had no room to pull more cables. Almost no room. He could pull a Cat5 through each of several chases. He saved 400 feet of 16-pair cable, installed in half the time. He gets IP audio and control over the same network, and he didn't have to hire union guys to do all that. He just did it himself. Indicative of the spirit of innovation that's been prevalent in public radio. Public radio has been an early adopter of AoIP. Let's see. This is Minnesota Public Radio. Sorry, my text is messed up here. So yeah, Minnesota Public Radio put in 14 studios or so worth. I think they're up to 20 now. Then KWMU in St. Louis put this in. And I thought I had some, okay. So this is Zach Harper. He's a Nashville-based IT pro, broadcast engineer. Let's see. He and a small team of engineers built a new high-profile studio for a nationwide morning show. They plan to expand later, but the focus was on building this one premier studio. So this is some of the Cumulus engineers building what became America's morning show from Cumulus. There they are building it, and there it is, mostly completed. And again, mostly completed. It's also outfitted for television, and that's the control room. And here it is in use. They do a morning show on the network there. But because they used this technology, they wanted to build a second studio for a show called Nash Nights. And they were able to literally run 1 Cat6 cable from the central wiring area to this new studio, and that's all the wiring that they had to run. Now they ran business phones and other stuff off other cables, but for the broadcast, it literally took 1 Cat6 cable. I think they ran 2, 1 for backup, but if you're pulling 1, you might as well pull 2. Anyway, it was very serendipitous the way it worked out. That's the crew on Nash Nights. I think there's a gentleman in this room that might recognize this picture. Bob Newberry's was the very first time I'd seen this work. Well, except at an NAB show, we had one working. But that was going 50 feet. How many miles is this? 4 miles?
5.
5 miles? Okay.
If I'd known it never been tried before, I probably wouldn't have done it.
Well, I think we said it would probably work. You built this as a backup STL because you had a...
Well, I funded it because of HT, the company of HT.
Oh, yeah. You needed more audio getting to the transmitter side.
Right.
Okay. But you ended up this being your main.
Yeah, oh yeah.
Because it sounds better.
Sounds better.
And the only problem with the other one, is Mosley, is that it has a 32 kilohertz low pass filter, right? I mean 32 kilohertz sampling. And this is 48 kilohertz sampling. And I didn't believe, when you demonstrated this, I didn't really, is it going to sound different? And you A, B between the Mosley system, which is linear. It's not compressed, right?
Right.
Yeah, it's a linear Mosley system, and this is linear. And I thought, there's not going to be a discernible difference. I mean, yeah, if you try to run a 18 kilohertz tone through the Mosley, it won't, and this will. But and so you A/B'd it, and I thought, it does sound better. I don't think it was the power of suggestion. I think it really did sound better.
You got all those free audio channels coming back the other way.
Oh yeah, for your HD monitoring, you can bring that back. Yeah.
I tried to use headphone monitoring through the processor at the transmitter site and back, but it didn't work.
No, because you're still running standard streams, and they have buffering in them. Another use, and by the way, thank you so much. I've gotten more mileage. Oh, sorry about this. I didn't know how far back I went. I've gotten more mileage out of your story, so that's been awesome. We have to go back to that barbecue place. What's it called? Dreamland, yeah. We do that sometime. So another, so someday I really think that Telos is going to be out of the codec business because we have connections now that don't need a codec. They work fine at audio linear bit rates. I mean, heck, they work fine at television bit rates. Of course they're going to work fine for audio. During the Olympics in Sochi, Russia, a lot of broadcasters went there bringing their ISDN gear, and it wasn't reliable because they had to pull out all the old Russian engineers to try to get ISDN to work. Swedish radio, though, decided to use there's a European broadcaster's IP network. I guess it's a bit like Vivix here in the US. It's a private network, and they just put a node, one of our nodes at one end, a node at the other end in Sweden, I think it was Sweden, and passed linear audio from Sochi to Sweden, no problem. 2.5 megabits per stereo stream, and you could run 2 monos on that. It'd be just fine because there's perfect separation between the two, and it worked great for the whole Olympics. So where we are today, well, Livewire's got a whole bunch of partners that speak Livewire. There's also the world of Ravenna, and then there's AES-67. And then there's other standards out there too. Wheatnet, Logitech, Lavo, SAS uses Dante, and there's Ravenna. And then there's all these Dante partners out there. And AWB, although I just read that AWB was actually going away now. There's just not enough interest in I'm sorry, AVB. AVB is going away. I don't always talk with other IP audio devices. When I do, I speak AES-67. So Telos was this guy right here, Greg Shea, who's our Chief Science Officer. Yes, we actually have that title. He was one of the founding people on the committee that developed AES-67. And a whole bunch of good folks on that committee. Mark Young with AES made the announcement of AES-67 being a standard. Oddly enough, he made the announcement on September 11th, but that was about 3 years ago, I think, that he made that announcement. So I'm going to skip through this. AES-67 has now been picked up by SMPTE as being the audio standard for their new video over IP standard. So AES-67 now has a huge proponent in the entire television industry. So that's all, it's here to stay. The one cool thing about AES-67 for a little manufacturer like us, or like Wheatstone, or Logitech, or even Lavo, is that if you were ever nervous about getting locked into something, oh, what if I buy Livewire and in 10 years I find that it's just passé, it's obsolete, and I've got to go to something else. And of course people experience that buying other digital products from other companies that's not even supported anymore. There's a lot of people out there with PR&E digital consoles that are hurting because they can't get support for it, or they have to pay for support for it. So AES-67, if nothing else, for Telos, it was like you can buy with confidence, because even if Livewire ends up not getting any more partners 10 years from now, we speak AES-67. And so you can certainly use that and talk to anything, or any other AES-67 device. So for the next little bit, I want to talk about why SIP and VoIP is really good for you as an engineer. Now that we're kind of established on the studio side of audio over IP, what can SIP and voice do for you? And I think if you play your cards right, it can make you look like not not only a team player, but make you look like a profit center instead of an expense center. Bob has some direct experience with this. I recall, Bob, you said you not really saved money, but you're doing a whole lot more than you were before, right. Whereas some other engineers have used it to really cut their expenses. All these organizations are using the Telos VX, and the presentation is a bit centric about this Telos VX multi-line, multi-studio talk show system, because it does so much, and it uses, if you're going to use a Telos VX, it forces you to save money. So, because you're going to have to go to a different telephone technology that you may have lollygagged about going to before. So here's some few typical installations of Telos VX systems at some radio stations. That's at WCBS in New York. That's at WCBS. That's in Tampa, at Cox Stations in Tampa. Forget where that is. That's in Atlanta. Yeah. What?
You've had CD decks.
Oh yeah.
Oh yeah.
Yeah. How about that? I'm trying to remember what station that was at. That may be in California, at some little mom and pop station in California. Okay. So why is SIP VoIP good for broadcasters? Well, I realize that a lot of us may get our impression of SIP and VoIP by the things that do go wrong. And of course, there's ways to do SIP and VoIP. Just like ISDN, a lot of people lamented the passing of ISDN because they thought it was very reliable. Hey, and as an engineer, your responsibility is limited. If you plug into that wall jack and it doesn't work, it ain't your problem. I mean, it may be your problem, but you get to call somebody else to fix it, right? With IP audio, if you plug it in and it doesn't work, it's still yours to figure out what's going wrong, or spend more money on more bandwidth or better quality of service or something like that. So I realize that with some engineers, I'm going out on a limb by saying it's better. It's better if it's used right, implemented properly, and you don't do things like try to run your business phone system off your business internet system, and on Friday afternoons people are uploading and downloading a whole bunch of stuff, and your phone calls sound like this. That's not well, actually that's what I do at my radio stations, but we're not uploading and downloading a whole lot of stuff on Friday afternoons. We tend to have enough bandwidth that it does work, and realize that nowadays even a lot of POTS lines are delivered via SIP. A lot of T1 lines are delivered via SIP, I should say via IP, and then converted into whatever old-fashioned technology that you want to use at your location. Properly managed, properly handled, this is fantastic. If you have problems with it, then it's a new learning set of what's going to go wrong. And back to the ISDN question, I spent some time talking to our support department at Telos. We've been dealing with ISDN questions for, what, 25 years now. And I said, do you guys still get a lot of ISDN support calls? Oh, yeah. Why? It's like fewer and fewer people are using it. Yeah, but it's getting worse and worse. I said, try to find somebody at the phone company who will believe you, send a tech out, do a bit error rate test. Can't find somebody until after the first of the year to work on it, whatever it may be. At least with IP, we have a lot of technicians coming into it. And, despite, all the political wranglings over net neutrality and over just the quality of your internet service, it really is just getting better and better and better over time.
It's getting harder for long distance services in ISDN.
Oh yeah, yeah. Yeah, exactly. But since more and more people, businesses, government agencies, banks depend on IP working properly, there's more pressure on companies, whether it's Comcast or Verizon or whomever or AT&T, to make it work properly. It's got to work better. So my own home service just keeps getting better. I keep getting higher speed, and I'm paying the same. Now, I can't imagine being a Comcast cheerleader, but they haven't done me wrong, and it just keeps getting better. You give it time. Yeah. Well, So in my neighborhood, Google Fiber supposedly is coming to Nashville. It's been coming to Nashville for 4 years now. But so around my neighborhood, in the last year we've had trucks and trucks and trucks and people running fiber and all these yellow jackets orange jackets going on the ends of cables all over the neighborhood. And one day there's an AT&T truck out there, and they're not known for their innovation really. And there's a little trailer there, and the cable coming down in the back of the trailer, and the guy must be in there working, and there's a security guard outside. So I pulled over. I said, "You guys are working your tails off here. What's going on?" And this guy, he worked for the security company. He didn't even work for AT&T, but he kind of knew the picture. And he said, "Yeah, we're rolling this up fast as we can." I said, "How come you guys didn't try to roll anything out for 40 years? What's the rush?" He said, "Competition. Comcast is doing this. Google's doing it. By God, we got to do it." Yep. And so when people complain about, hey, there's only one provider there's only one ISP in my neighborhood. Well, that may be your town council's fault, not the FCC's fault, because there's a lot of barriers to entry for being an ISP. So anyway, enough of that. You do get better call quality, even on a G711 call. But you can also get G722 or other HD voice, and I realize I got a room full of engineers here, so when I say HD, first of all, you kind of go, yeah, we were told that about HD radio. And now, HD voice, come on, Kirk, what is that? Well, HD voice is the telephone industry's acronym or marketing term for approximately 7.5 kilohertz audio. Now, for a telephone, that is awfully good. I will tell you that about 3 or 4 years ago, probably 4 years ago, T-Mobile, which is my phone carrier, they were the first to implement the AMR wideband codec throughout their network. And if you had a phone that spoke AMR wideband and you were calling another T-Mobile phone that also spoke AMR wideband, you got this really nice connection. And I would say, and it's absolutely true, that my wife had an iPhone iPhone 5, which is the first one, and only the T-Mobile iPhone 5 supported AMR wideband at that point. And I had a new Samsung Galaxy Note 4, their first phone that supported AMR wideband on the T-Mobile network. And I would call her, and for the first time in my life, I could understand my wife's mumbling. and between the better codec, and by the way, the phone companies have got to love AMR wideband, except maybe, whoops, I didn't mean to do that, except for the royalties they have to pay to use it, because it can operate, it's a variable rate codec, so if they can only give you 6 kilobits per second, it'll work at 6 kilobits per second. The highest it works at, I think, is 22 kilobits per second, so it's not a hog, not like G722, which is 64. Even G711 is 64 kilobits. Of course, your cell phone doesn't use those. They used other lower bitrate codecs, which is partly why they sounded bad. But you can do broadcast remotes with AMR wideband. And you can do, I wouldn't do a music concert, but you can do sports remotes with G722. I realize for us broadcasters, it's like Plan C, but G722 is very ubiquitous. It's easy to implement. It's pretty well cost-free, as I believe, and it's in the Telos VX phone system. And it's in free or cheap software for your phone. Anyway, there's your audio bandwidth difference, G711 and G722, and of course they both take the same bit rate, 64 kilobits. By the time you add packetizing, you're up to about, I think, 88 kilobits per second is what I usually measure for a G711 or G722 phone call that's IP. Okay, so we talked about HD voice. You can get practical limit of a VX is 12 lines on a show. I think one of our call screening partners lets you do 24 lines on a show, but not with a physical controller, with his on-screen, touchscreen if you like, controller. So you can have, that's the idea, you assign a line to a show, and then you have faders. You can have, okay, this says up to 25 console faders or caller outputs in use at the same time. That's what takes a lot of resources, because we do audio processing on every caller. We can provide complete conferencing and mix minus in our system. So if you have a show of 12 lines and you got one of them on the air, let's say you have 3 of them on the air. You give us one mix minus, we provide the proper mix minus for each of those 3 callers. So we're actually doing a lot of math, a lot of audio in that. You can also turn on acoustic echo cancellation, which is a Fraunhofer algorithm, and that lets you have a TV studio with open mic, open speakers, and you can literally have the caller coming out of a speaker, take the microphone and put it right up on the speaker, and it won't feed back. And it won't go whop, 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 whop. It's really smart. It takes a lot of resources in the Telos VX to do that. So a typical station cluster allocation will have maybe 8 control rooms, 2 faders in each one, 5 prod rooms, 1 fader, and 4 call screeners. So each of those, remember Ruth Buzzy? No, that wasn't Ruth Buzzy. That was Lily. What was her name though? Ernestine. That's right. That's right. That's right. By the way, who was I talking to about Paducah, Kentucky earlier? She's from that area. Yeah, yeah. There's a. In fact, there's a. Don't ask me why I know this. There's a lingerie store in Paducah called Sans Souci. I've never been in there. It was across the street from the lunchroom we had a trade with. Yeah. And anyway, she owned that lingerie store, so I was told. So VX system architecture looks like this. Let's see, there's the VX engine. There's your gateway or other SIP source, and then it just goes into your network that talks to your hopefully existing Axia devices. If you don't have Axia, then you're going to add an Ethernet switch to the mix engine and a couple of nodes and wire those into the stuff that you need. Oh, and these VX VSETs are going to connect to that as well. And your call screener. Whoops, how did I do that? Okay. Yeah, that's nice. Okay. How can you bring phone lines into your VX? And to me, this is, if you call our support department and you've got a problem with configuring the Axia side of this, the live wire side, we can help you like that. We know all about this. We know exactly, if you tell us what you got, we know exactly what you got. But whatever's on the WAN side of things is often a mystery. And you ask 5 people at your phone company or your other provider, they get 6 answers. So the tough part of implementing one of these is figuring that side out, the part that connects, because it's not just, a POTS line you plug in, dial tone, okay, great, got battery voltage, you get a dial tone. May or may not have a long distance provider hooked up. If you didn't, then you could still make long distance calls. They would just cost you an arm and a leg, right? Bob, did you experience difficulty?
Oh,
yeah.
It's a mystery to the provider as well.
Yeah, there you go. That's the problem. It's a mystery to the provider. But you got it worked out.
Yeah, our first implementation was in Gadsden, fortunately, and I had all the time in the world to figure it out with Windstream, our provider.
Gotcha.
They gave us several examples. Try this, try this, try this. We found another asterisk user. He does this, and I just sat there and bingo. When it worked, it worked. It's been working ever since.
And you don't touch it then. You save the configuration and hope the phone company doesn't change theirs.
Yeah.
Yeah. So we'll just we'll look over these 5 different ways to connect to get SIP into your system. One way is let's see. Well, I cover these individually, so let's just start with this. You can convert existing lines to SIP using a gateway device. Honestly, 7 or 8 years ago, we thought this would be a really good idea, and now it turns out it's not a good idea, because these gateway devices are just crap. They're just awful. And we picked a company called PENCHANT, a U.S. manufacturer in the Baltimore, Maryland area, seemed to have their act together, and it's still. And PENCHANT had this business model kind of like Sonic Wall. You couldn't call them and ask a question. You had to deal with one of their dealers who was free to charge you whatever he wanted to answer your question. So we sent our guys to PENCHANT to become authorized, consultants, authorized patent consultants. And and just little things like their clock was not, their sampling wasn't 8 kilohertz. It was not 8 kilohertz. It was something close, but not 8 kilohertz. So we get all these little glitches and anomalies. And then we found, for a few customers, insisted on keeping their POTS lines. We're not going to move to SIP. Got to keep the POTS lines. So we put in some big, honking, expensive patent gateways to convert POTS to SIP. And after a year, they said, we're ready for SIP. We're ready to then they had a few problems. We got those pretty much solved for them, but still they said, one of the problems of switching from POTS to SIP is probably whoever your incumbent provider is. Because if you're on a choke line, they may tell you, we can't port those over, we can't give them to another company, and maybe they can't, but in some markets they can. So I want to tell you a very important little story about the greater media stations in Detroit. And they have a sports talk station, I forget the call sign, but big users of telephone, a lot of caller interaction on these stations, so part of the community. And they moved over to a VX system, and they wanted to, of course, port their 4 decades old request numbers over to the new system. Okay, well, we'll get some new numbers. Can we maybe port those to a PRI? Oh, actually, you know what? They were on PRI. Anywhere else. We won't move them to another company, and we won't provide them on SIP. You can have it on PRI. But the PRI was costing about $1,200 a month. So what they ended up doing, oh, and they said, well, will you at least provide an intercept message? The new number is, said, no, we can't do that. It's on a choke network. We can't do that. Can we call forward? No, no. And by the way, I've run into other stations where the day they went to cut over, they hit the call forward code. Oh, that doesn't work on choke lines. So, and again, it may vary by market, but Detroit was particularly bad. So what WRIF, what the greater media stations did was they dedicated an asterisk phone system to their incoming phone lines. And it just answered the phone saying, hey, thanks for calling WRIF, Rock 101 or whatever. Hey, we've got a brand new phone number. Why don't you write it down? We'd love to hear from you, blah, 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 blah. Again, thanks for calling, and again, here's the new number. So they had a count, and they had call logging, so they had a count of how many people called the old line. And of course, on the air, they're given the new number, which was from a third-party provider, which was cheap as dirt, worked great, toll-free for everybody, didn't cost the station much at all, and they saw the calls on the old numbers just drop off precipitously. It wasn't important. The old number, I mean, you know, I've called the talk show a few times because I'm not opinionated on anything, and I can't call the show until they give the number on the air. I don't know what the number is. You know, it's the immediacy. Now, sure, you may have bumper stickers or refrigerator magnets or stuff like that out there in the market with your old phone number, so you may have to keep that around for a while. But I think that after 6 months, they dropped their PRIs. And they said, we didn't have to keep it 6 months. I mean, I want to say, I kind of remember, after 2 or 3 weeks, it was like down to nothing.
That's more of a programmer, that seems to be more of a programmer mindset, that everybody has your call-in number memorized.
Yes.
And they have it all saved in their phone and whatever.
No.
In today's day and age, your station isn't that important.
Yeah, yeah.
They listen to the number listen for the number on the air, that's the number they call. Because like iHeart stations, and everybody else that does national contesting, during the course of any given day, they might give out 4 different phone numbers.
Ah, yeah.
Whether it's a national toll-free number, a regional toll-free number,
Yep.
the local station number, the business number. People call the number you tell them to call. They're not memorizing or anything anymore. You ask somebody, hey, what's your mother's phone number? Oh, I don't know, I'll save it on my phone.
Yeah.
If they don't know their mother's number, they're still not going to know yours.
So how many, y'all have been in engineering as long as I have, how many of you, I used to have 200 phone numbers memorized in my head. And I had a little black book for the others that I couldn't memorize, but if I want to call ABC Radio Master Control in New York, I knew the number. If I need to call Jeff at Allied within the satellite department, what was his name? Jeff who? Jeff Nordstrom, yes, yes. I knew his number. So anyway, yeah. Okay, yes, exactly. Okay, you can convert existing lines to SIP using an asterisk SIP server. So with asterisk-based PBXs, and by the way, and you know, this can be anything, that's your new phone system. Now, I don't really recommend it, but the latest Raspberry Pi 3, this is an older one, but I keep reading, it has equivalent capability of about $1,000 appliance, phone system. You can easily run a doctor's, you can run a radio station off it, just not a high volume request lines. You know, the hardest thing a radio station phone system has to do is say no to additional connection requests. No, 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 I'm full. No, but I would do that, except the micro USB connector makes me a little nervous about powering that sucker. But yeah, you can run a phone system off of that with no problem. Or you can easily spend $2,000, $3,000, $4,000, $10,000 on nice computer server grade equipment. You know, what a lot of people do is they buy a refurbished Dell or HP server and load an Asterisk-based PBX implementation on it. Point I was going to make here is you can also get cards from, is it Digium. You can get POTS cards, PRI cards. Yeah. So if whatever, you're not ready to actually go whole hog with SIP, you can bring your lines in on a card that then gets converted. And the Asterisk-based PBX gives you a lot of functionality you didn't have before that the VX doesn't give you either. Never got around to the graphic I thought I was going to get. Yeah, it's got to be coming up. Okay. Whoops. Yeah. So that's a second way, traditional telco into an Asterisk PBX. You can get SIP lines off a business PBX, with the caveat that you may be asked to pay license fees, in which case you'll become very interested in just doing your own. You can get a dedicated IP connection from Verizon, AT&T, Windstream, XO Communications. They will either arrange for or bring new copper or fiber into your building. Now, if you're in a downtown area where such things exist, great. This would then be managed service. This wouldn't have other stuff on it. This would be every bit as good as what you're used to a T1 or POTS or PRI being, because it's totally managed. There's not a bunch of other stuff on it. It's your phone calls. And by the way, I show that going into the VX. Really, you'd bring that into an Asterisk. The VX can handle by the way, trunks and extensions. Trunks are from one PBX to another PBX connections. That's what a trunk is in the SIP world. An extension is a PBX to an end device. The VX, I hope I have a graphic later, the VX is a whole collection of end devices. It's not a PBX. It's a bunch of phones in software, and then with a bunch of audio processing and management of groups all in there, and a bunch of audio routing, music on hold, that kind of stuff. Next, you can get cloud SIP. This is what Art Bell does. This is what, if you get Grasshopper service, for example, that's cloud-based PBX. I'm sorry, you know what, I should differentiate. There's actually two different ways to do this. There's cloud SIP, like I have a line with Vitality. Vitality doesn't provide PBX services for me. They provide me a trunk line that I can terminate with a Raspberry Pi, and then make an extension off the Raspberry Pi to my VX. But you can also get cloud PBX. So there's cloud trunk lines and cloud-based extensions where your PBX is actually in the cloud. Whenever I get a new employee at my stations at Delta Radio in Mississippi, I log into a server in Denver and add the extension, the person's name, get them to record their voicemail message and all that kind of stuff. Now, VX can get its SIP sources from several different places at once. So you can have some lines from those different sources at the same time. And that's key, because that lets you do something really cool. So you could get some lines from each of these at the same time. If you had to keep a couple of POTS lines with your old number to make your PD happy, you could do that and get other lines from elsewhere. So your phone lines come in. Oh, now we got to talk about multiple studios and how that works out. Let's see. What was my point here? Well, I guess you get the idea. Multiple studios can run off of a single Telos VX, and then you can have some call screener phones, and they can associate with any of those shows or studios. So what I want to show you now, okay, here we go. This is the graphic I've been waiting on. What's inside? Well, inside the VX, first of all, is a pool of phone lines or extensions. And again, these come in as SIP, and they're not trunks. They need to be extensions off of some other PBX. Then we have to define what's in the studio. And that means we have to define what equipment is in the studio so we know how many outputs we can have at once. Is it one fader? Is it one hybrid, if you will? Is it 2 faders? Is it 10 faders? What exists in that studio? Also GPIO. We have to know what GPIO is associated with that studio. So we have to define, and we can have fixed lines, and we can have hunt lines. And we have live wire channels associated with that studio for the audio in and out of that studio. Mix minus and the program on hold. and if we do acoustic echo cancellation. So that's all fixed per studio. You're going to define that. Otherwise, you have to tell the VX what exists in that studio. Then, after that's done, after the VX knows about what live wire channels and GPIO channels are there, then you can define a show. So we have our phone lines coming in. We know what our studios look like in terms of their I's and O's. And then we define which phone lines get used for a particular show. Now that implies that we can define a show and use it in one studio, and the next day use the same show in a different studio. So those phone lines are transportable to different studio. Now if you define a show as a 12-line show, and then you move it over to a studio with 6 lines, guess what? You can't have 12 lines on a 6-line phone. So I forget exactly how that works, but obviously you can't get the other 6 lines in there. But you can make the shows portable. You can define hunt groups this way. You can define when you busy all, which lines actually get busied, per show. So that's what makes the system really flexible, is those 3 definitions. And I kind of show how that works here. So let's say we have a Titan Sports Super something, what is that? I don't know. Light FM, Morning Mayhem, and Kirk's Morning Show. And so there's how our lines are divvied up. But for whatever reason, we got to switch studios. You can portable these shows like this, and they'll work just like they did in the previous room. You can select which shows you're going to use in a given studio just by selecting that on any phone that is associated with any VSET that's associated with that room. So let's see if we have here. We talked about we already talked about how to size this for a studio. I'm not going to go through all this because I want, with a little bit of remaining time, I want to. How many VSETs do you need? How many people are going to be call screening? How many people need to pick up a line? Different call management software is available. This is from Telos. It's free, and I don't really know if it's supported much anymore because now we have this software, X-Screen Lite. This is from our friends in England. It comes free with it. And then there's a couple other brands. This is from France, and I forget whose that is. When you're thinking about doing this, you've got to talk to us. Salespeople at any of our dealers don't know enough to really help you out. So we have 2 Joes in our company, Joe Talbot and Joe Mauck. And both of these are telephony gurus. And they really, really want to talk to you before you place an order because they want to make sure you've ordered the right stuff. Here a second. So one of the latest applications has been using VX for television for doing remotes. The level of savings of moving to SIP can really make this thing pay off in 18 months, a couple of years at the most. You bring up a good point in that as engineers, we've kind of thought about phone system as a per room proposition, right? And so it looks like kind of a big step to go to a multi-room deal. Well, the manager doesn't want me to spend. I mean, a Telos VX system is gonna be at least $10,000 or $11,000. And if you got multiple studios, it's going to be more than that. But per studio, if you already have Axia, this is like half to 2/3 the price of putting new phone systems in each room.
Through Digium back to POTS into a 2x12.
So this has surprised a lot of people actually. Why would G711 over SIP sound better than G711 over POTS? Because it's the same codec, right?
Right.
And I can't say that I've had a great explanation other than you don't have any more conversions. You don't have any of the problems you would have with analog. The Asterisk system can do lots of things though. They wanted I think there they called it their prayer line, but it was a conference line. They wanted reporters to be able to call into a conference line and
You described a single point, a core. What if you lose that core? That's the single point of failure for now you kind of touched on it in that crack facility.
Yeah.
But how do you address a single point of failure in an Axia facility?
And this is something that a number of Axia customers have implemented various methods to have redundancy. And it really boils down to redundancy. Do you want to have hot redundancy? And Cisco does have some methods for automatic moving of stuff over. I'm not familiar with what they are. I just know that they do, like the one in Prague. It doesn't take a Cisco 6500 switch to operate two in parallel. You can have a much lesser switch. Some stations, like Minnesota Public Radio, they would have 3 Cisco switches, and they would distribute devices across 2 of them, and so they have an N+1. And if one of them died, instead of doing all the smart switching between, they would just figure out which one died and move those cables to the other switch. And within a couple of minutes, everything would they'd find each other again, and they'd be back on the air again. If a central core switch dies, all of the switches that were edge switches now become their own core switches. So let's say that you've got 5 studios on this switch, and 5 studios on that switch, and 5 studios on that switch, and those switches feed to a common switch. If that common switch dies, everything that these 5 studios could do before, not involving the central switch, they can still do. And that's why some people have run like, well, I'm going to take an analog feed out of this console, out of a local node, and I'm going to run that back to my rack room and at least be able to have that. WOR did that. They never had to use it, but they ran 2 Cat 5s or 2 Cat 6s to each studio, and one of them was their IP, and the other one was for just a back feed of analog audio from that studio back to the rack room. Now, if they lost that, well, they'd also lose their NX12 phone system that was in the rack room tied in through Axia. In American Samoa, my little radio stations there, we just moved our stations. And we have 2 core switches, and our edge switches are switches. Oh, I didn't even show you. On some of our consoles, there's a switch built into the console because it's just real easy for us to do that. And so, obviously, if that switch dies, it's the same thing as the console dying. But in our rack room, I bought 2 Cisco switches and configured them exactly the same. Now, American Samoa is hard to get to. And shipping something there, there's no overnight shipping. Quickest that stuff's going to get there is 3-4 days. So I just bought 2 Cisco switches from eBay, and they're fine. And I wiped their memory, and we reconfigured them, and that took some guy in support at Telos literally 12 minutes to configure both of them remotely. I gave him remote access. So I shipped them to Samoa. Now, so I've got a hot one and a standby one. And our manager and a couple other people know that if that ever dies, if it ever looks like, hey, nothing's working now, we'll just turn the other one on and move these 7 cables or whatever it is over to the new one, and you're back on. And by the way, we tested it. So.
You mentioned that the core switch handles a route until someone asks for it. So you're saying once that route's established, the core is not even considered anymore at that point? So that's where I'm getting hung, because it seemed like the core held that route until
okay. So the edge switches, of course, they can no longer see anything that was in the central rack room if they're not part of that. But the edge switches, each one then will become its own IGMP querier. I should explain, when you set up an Axia network, the switch that has the lowest IP address becomes the IGMP querier. So you need to make sure that the switches you're going to consider your core switches have the lowest IP addresses. So if you've got an edge switch that's talking to several studios, and its core switch goes away, then all of a sudden it has the lowest IP address, and it becomes the querier for the rooms that it's serving. And so the tables all get rebuilt in a matter of, I think worst case time is going to be 30 or 40 seconds. And so, yeah, that all gets rebuilt. I am about to find.
This. Kirk, as a point of reference, at our facility, we ended up, all the edge switches are cross-connected to 2 central core switches, which are redundant for each other. So if the primary core switch fails, then the secondary picks up all the virtual routing. It's all done virtually. Hot standby route redundancy protocol, HSRP. And so if the primary router, the layer 3 router dies, then backup picks it up, and you can do that same thing with IGMP as well, so it can pick it up. But then the switch still has a connection back to the core, which would still feed out to the rest of the facility.
Okay.
But it involves double core switches and double runs from each switch back to the double core. If that makes sense. It's a cross matrix, so you have 2 core switches, and each edge has 2 feeds back. So that if each core switch is connected to all of the central.
So are you managing port loop back or fold back through that redundancy software you mentioned?
No.
How do you do that without getting a loop?
Spanning tree protocol. Spanning tree protocol helps prune off anything that's got 2 paths. And what happens is it picks a primary path to the central switch at the highest precedence or best switch, and then fails over to the secondary if that primary becomes unavailable after that time. It gets into the IT side of the broadcast. That's really wrong.
So I've got a little short 3-minute video, and this will be the last thing we look at, because Martin is going to tell you about an interesting use case. We were there for a while. Let's see how loud the audio does here.
It's right now, but by using Telos VX's ability.
Okay, so what he's going to talk about, the Cox stations in Tampa, using a soft phone that does G722. That soft phone, for all their employees, they're registered as extensions on their Asterisk phone system, which feeds the Telos VX. The VX natively also speaks G722. So any of their employees can open the soft phone, they become registered, they dial an extension in whatever control room they want to talk to, and hit send. When the guy in there picks up, they're talking with 7.5 kilohertz of audio quality. And so they can go do live remotes that are not irritating on the air. You could even do long-form audio at 7.5 kilohertz, well, as long as it's not music. And actually, the G722 codec is really not an irritating codec compared to other perceptual codecs. It's not very perceptual. So anyway, I didn't realize how much TV stations, especially active ones, like WSB in Atlanta, use IFB. They may have 30 or 40 IFB connections at the same time. A single truck may have 3 or 4 people, each with their own IFB. So anyway, rather than putting you through the 35-minute talk, here's the 3-minute talk about this.
Device right now, but by using Telos VX's ability to communicate using HD voice, intelligibility to producers, talent, directors and engineers in the field has never been better, never been more reliable. Hi, this is Martin Dicer from the Telos Alliance. TV broadcasters around the world have been relying on POTS telephone lines and ISDN codecs for many years to provide their backhaul communications, IFBs to the field, remote cohorts, and also contribution. That's all changing with the use of the Telos VX broadcast VoIP engine. It's a broadcast VoIP interface that provides scalability and flexibility in the fast-paced world of television production. Particularly in news and sports, the Telos VX provides up to 24 lines of communication with your field operational staff. It can be used for IFBs, remote cohorts, it can be used for contribution and even conferencing. Many broadcasters around the world are discovering the flexibility of the Telos VX and employing it in their plant to replace outdated analog and ISDN equipment. The Telos VX VoIP engine is a 2RU box with dual power supplies for resilience, dual gigabit Ethernet ports for connection to your SIP PBX and also to your audio over IP network. At only 2 rack units high, the Telos VX can replace up to 12 rack units of dual couplers, providing space saving and cost saving. Telos VX integrates with your audio production facilities, with your intercom systems, and allows producers and directors to communicate directly with your staff in the field. These can be your reporters, your cameramen, your engineering staff, and even eyewitnesses who pick up on a story that's happening right outside their house. VIP callers can call directly into the station, and because the Telos VX provides broadcast quality contribution audio directly through its AoIP streaming, it can be taken straight to the console and straight to air. Because the Telos VX connects over audio over IP using the LiveWire Plus AS67 interoperability standard, 48K 24-bit program quality audio is at hand for producers and directors to take those callers direct to air. With direct connectivity using SIP to your business telephone system, a caller into the station can be transferred from the house exchange straight into the broadcast network, taken straight to air. Integrating seamlessly into your communications system and to your broadcast production audio system, mix minuses and reverse feeds can be routed straight through the VX and straight out into the field and into the earpieces and headphones of the production staff that matter. Telos VX is your one-stop shop for broadcast telecommunications. I invite you to visit us at www.telosalliance.com to learn more about how Telos VX can save you money, can improve your workflow, and can make TV production easier than ever before.